Okay, in this vodcast, what we're going to do is take a look at the Bohr model of the atom, and we're going to start looking at the quantum model of the atom. The important thing, well, there's many important things about the Bohr model, but the one thing I want to emphasize right now is that the Bohr model of the atom is the link between what we call the classical model. In other words, we could think of Rutherford's model of the atom and the quantum model. So you've got the Rutherford model here, and that uses classical, let's just call it classical physics at this point. Then we've got the quantum model over here, which uses quantum mechanics. Well, the Bohr model of the atom is kind of the link between these two models. In other words, Bohr's model takes it past the classical model, but not quite to the quantum model. So as you could probably tell by now, these models all lead to one another. So anyway, let's take a look at the difference between the Rutherford model of the atom and the Bohr model. If you remember from our previous unit, Rutherford basically said that the nucleus of the atom is very dense. It's where I should say just about all of the mass is located. And then he said the electrons are outside that nucleus. Rutherford didn't say anything about where those electrons were or what was keeping them outside the nucleus. And everybody knew, including Rutherford, that there was a problem here. In other words, if electrons are negatively charged, and he knew that that nucleus was positively charged, these electrons would eventually lose energy and fall into the nucleus and annihilate each other. And Rutherford understood this problem, and he knew that this was going to be an issue. Well, Bohr came along, and Bohr was actually a student of Rutherford's. Bohr came along and solved the problem, and he started looking at the atom in terms of light. And we'll talk about that more in a later vodcast, but basically what Bohr did was he took these electrons, and instead of just having them outside the nucleus randomly, these electrons are now assigned to what we call energy levels. The designation for the energy level is N. So you can see N is equal to 1, N is equal to 2. And these electrons are confined to those energy levels unless you put some energy into them to make them jump to a new energy level. But the key to Bohr's model was you had to put a specific amount of energy into that electron. In other words, think of it as climbing a ladder. You've got your ladder here. To get your foot to the next rung, you have to put in a specific amount of energy or a specific distance. If you only went halfway, your foot wouldn't make it to the next rung. And Bohr's model worked sort of like that. In other words, each energy level has a specific energy. As you move away from the nucleus, the overall energy of those levels gets greater, but then what you'll see is the steps in between each level get smaller. And that's an important point, that the amount of energy to go from the first to the second energy level, in other words, to go from 1 to 2, is a greater jump than to go from 2 to 3, etc. Okay, so let's take a little bit closer look at Bohr's model. Okay, when you take physics, or if you've already taken physics, you'll talk a lot about Einstein. Arguably the most famous scientist ever, definitely the most famous science in the modern age. And we won't talk much about what Einstein did, unfortunately, but what we want to mention right here is that Einstein did some experiments, or did some thought experiments with the photoelectric effect. And basically what he found was that if you shine light on a metal surface, what's going to happen is you're going to eject electrons off of that surface. And what Einstein found was that these electrons are in little packets. In other words, they're individual particles of light. So what we could say is the atom is to matter, the photon is to light. So what Einstein started looking at was, is light a particle or does it behave as a wave? Because up until that time, everybody assumed that light traveled as a wave. But now it's showing particle characteristics also. Well, Bohr took some of the work that Einstein did and started looking at the hydrogen atom. And what Bohr did was he came up with a mathematical model for the hydrogen atom. And it put the nucleus at the center, and it's positively charged, and then it puts those electrons in energy levels with specific energies around that nucleus. And that is a heck of a circle. Okay, there's a lot more detail to the Bohr model of the atom, but what we're going to do is move on a little bit and talk about how this applies to what we'll do. Okay. So now we have, what we want to do is start looking at the atom in terms of electromagnetic radiation. And when we say electromagnetic radiation, we basically mean light. So what we're finding is that light behaves as a wave, but it also behaves as a photon. And what we call that is the wave particle duality of light. Now that's going to be important later on, especially if you were to take physics. But what we're going to do is start treating the electron as a wave. And this is going to be the link, or this is going to be the next step in atomic theory. Before we do that, let's start taking a little bit closer look at light waves. What we'll say the nature of waves. First of all, waves travel in this form, which I'm sure you've seen before. And we call that top part the crest. We call the bottom of the wave the trough. The middle of the wave we call the node. So if you go from crest to crest or trough to trough, we're going to call that the length or the wavelength. And it gets the symbol, the Greek symbol lambda. If those wavelengths start getting closer together, what happens is they will go by a single point quicker. So in other words, let's say this wave is traveling in that direction, and you have some sort of timer here that can count each time one of these waves passes the timer. If your wavelength is smaller, more of those points are going to go past your timer in the same amount of time. That is what we call frequency. So frequency is going to be the number of waves that passes a point in a second. And its Greek symbol is that, and we call that nu. So that is lambda, and that is nu. The units for wavelength we're going to measure in meters, and the units for frequency are inverse seconds. And again, it stands for how many times the wave passes per second, or I should say how many waves pass per second. Okay, let's take a look at the electromagnetic spectrum, and hopefully you've seen one of these from Earth and Space Science. So as light travels, different wavelengths have different frequencies, which we just showed in the last diagram, but different wavelengths then correspond to different colors on the rainbow. And that's where we get Roy, G, Biv. Red light, orange, yellow, green, blue, indigo, and violet. We're not going to memorize all these, but what you would want to know about this is that red light has the longest, we could spell it right, red light has the longest wavelength and the lowest frequency. Violet light would have the shortest wavelength and the highest frequency. So as you look at the electromagnetic spectrum, you could say as wavelength increases, frequency decreases, and vice versa. Now the other thing we're going to look at is energy. Energy gets the symbol E. It has the units joules. J stands for joules. And as wavelength increases, energy decreases. So as energy decreases, frequency decreases. So there's a relationship between energy, wavelength, and frequency. And you should know those relationships. Alright, so what does all of this have to do with the Bohr model of the atom? Well, what we want to do is start looking at why certain elements exhibit what we call emission spectra, which means they emit different colors of light. And again, we'll talk in more detail about this. So if you look at the Bohr model of the atom, remember what we said was that those energy levels go out 1, 2, 3, 4, 5, etc. So and this diagram doesn't show it, but this one does. The jump from 1 to 2 is big, 2 to 3 is smaller, 3 to 4 is even smaller. If those jumps correspond to energy, each one of those energies has a corresponding wavelength. Because remember, energy, wavelength, and frequency are related. So if the energy is different between those jumps, the wavelength would be different, which means the color of light would be different. So what this means is if you had an electron in the second energy level and it fell to the first energy level, it would emit a certain energy of light at a certain wavelength or color. So the question might be, well, why would an electron fall from the second to the first? Well, what happens is if you put energy into the electron, in other words, you put the chemical over a fire or put an electrical charge through it, those electrons jump up to higher energy levels, and once they jump up, they fall back down again. As they fall, they release the amount of energy that it took to get them to jump to the higher energy level. So each fall from different levels releases a different color of light. So what we end up with is called an emission spectra. What you want to know about emission spectra right now is that each atom has its own specific emission spectra. We say the emission spectra is the fingerprint of the atom. In other words, hydrogen might have an emission spectra that looks like that. Heliums would look a little bit different. Lithiums would even look different. And the reason is because each atom has a different number of electrons around it which can jump to different levels and fall back to different levels, thus giving different energies of light or different spectrum. Alright, so let's just go through the three models real quick. Thomson came up with what we call the plum pudding model. In other words, he said the atom was just a, for lack of a better word, a blob, with positives and negatives distributed throughout the atom. No real structure, though, or at least he didn't define a structure. Rutherford said the nucleus was dense, positively charged, and the electrons were way outside the nucleus. But again, didn't say anything about where those electrons were. In the Bohr model of the atom, same dense nucleus as Rutherford's model, but the difference being those electrons are now in energy levels assigned to specific energy level, or assigned to specific energies for each level. As the levels get away from the nucleus, the overall energy increases, but the jumps between levels get smaller and smaller. And what we're going to do in the next couple of vodcasts is investigate this whole notion of the Bohr model of the atom leading to the quantum model more thoroughly.